Hello, my name is Victor, and me and my team we are going to talk about the particle X17. But first, we need to review some previous information, which is the standard model. The standard model it has been given that name since the year 1970, but it is a theory that has been developed by the effort of many generations of scientists long time ago. This theory puts the forces and the matter into one same concept called particles, and from here particles are divided into two types, fermions and bosons. Fermions build up all matter that we know of its existence, such as you and me. And fermions are divided into two types, quarks and leptons. There are more divisions between these two levels, but for the purpose of the video, we're going to skip it and going directly to the most fundamental particles. And well, for quarks, there are 6 types: up, down, strange, top, and bottom. And here are born the protons and the neutrons, and depending on which type of quarks are you combining in. And then the leptons, we can here identify the electron and the muon and tau. And there's also neutrons, which there are 3 types: electron neutrons, muon neutrons, and tau neutrons. All these particles have been discovered or proved its existence by experiments. And once said that, there exist also the bosons particles, which are the particles that carry the forces. The electromagnetic force is carried by the photon boson, and for the weak force is the W plus and W minus and C boson. For the strong force is the gluon boson, and as well these have been proved experimentally, and it is even more surprisingly that they have same properties. They can be described with the same properties as these particles, such as mass, electrical charge, decay, and also spin. And these characteristics decide whether the bosons interact with fermions or not. Now, gravity cannot be part of this standard model because of many reasons, and it does not fit on this theory. But recently, scientists have discovered a new type of force, a new type of boson called particle X17, which the scientists don't know 100% for sure if it's gonna fit on this theory, and if it might be the case that it is gonna be needed a new physical fundamental theory from scratch to be created. But the good news is that it can be, if it exists, this particle, it can be the possibility that there is an open window for some physical entities that we haven't understood yet, such as the dark matter.
What we have already heard about physics of particles, it's important to have a really clear concept about what an action and a boson means. This in order to have a deeper understanding in what is the X17 particle. The particle X17 is an hypothetical subatomic particle proposed by Attila and his team of nuclear physicists in Hungary, in order to explain some anomalous measurement results in their experiments. The particle was proposed to explain wide angles observed in the trajectory paths of particles produced during a nucleus of helium-8 atoms transition. That was in 2015. After that, they once observed the same phenomena in stable helium atoms in 2019. The particle X17 has been described as a particle photophobic, means it ignores protons. X boson with a mass approximately of 17 mega electron volts, that is around 34 times the mass of the electron. The X17 particle could be the force carrier for a postulate of the 5th force, possibly connected with dark matter. In summary, if Hungarian scientists have found a brand new boson, it subsequently means that they have found a brand new fundamental force as well, although its properties are still unknown.
Hi, my name is Manuel Muñoz, and I'm going to explain the experimental part of the X17 particle theory, and that's the atomic experiment. The experiment was performed at 5 megavolts Van de Graaff accelerator in Debrecen. It consisted on aiming some proton beams to hit a lithium tungsten that generates a high-energy beryllium atom plus the X17 particle that later decays into a positron and an electron. And this result is measured by the atom key per spectrometer that you can see here in the right side of the screen. The center of it is the target surrounded by multiple multi-wire proportional counters. That's a device that is keeping track and record of the position the particle hits, plus 5 detector telescopes that are actually selenators. These are selenators because they depend on the selenation property. That means that every time a particle passes, a flash of light is produced. So this is a basic diagram of a selenator, and the particle enters either the positron or the electron, interacts and goes out of this chamber, goes out of this track, and ends up giving us some current and voltage as an output that we can easily relate with the particle energy. These were the results obtained from the experiment. These are some graphs that are going to be better explained later. And these are some similar experiments. The Na48/2, that where this was looking for the same to prove there exist some dark photons, but this was based on the reaction of the decay of a neutral pion. But this was already cancelled because no positive results were found on this one. And the Na64 that's currently working at the CERN. And the latest results were obtained because the atom key team repeated the experiment, but instead of a beryllium atom, they used the helium atom. So the complete reaction with this, with the same middle step, they obtained the same results we already obtained in the beryllium atom.
Hi, I'm Mauricio, and I'm going to talk about the statistical interpretation of the results and the correlation with the relativity and the wave function. Of course, first of all, we have to understand the results. We bombard the helium or beryllium for experiments, and there's a conservation of momentum, liberating a photon and an anti-electron and an electron. But also, we need to think about as a wave, because the results are interpreted or are pointed out as a correlation with the angle, and that can be explained as a scattering of the electron and anti-electron. That's why there are some angles that the energy of the anti-electron and electron are higher than other angles. In this graph is represented the scatter pattern of the electrons and anti-electrons with respect of the angle. The curve with red dots represents the results of the experiment, and the blue line with black dots represents the background anti-electron and electron pairs. As the experiment consists of a big amount of tests, the assumed distribution of the error is a normal distribution. We can see that an angle around 120 degrees, the expected value of the exponential decrease, and the results are different. The significance of this difference is around 7.2 standard deviation, so the probability of the result to be considered an statistical error is practically null. So something new is happening at the angle, and the result has the statistical proof to be considered a discovery. But I don't quite understand what's the meaning of this anti-electron and electron pair. Well, this background, the meaning is the cosmic radiation. There's like a trace of the Big Bang that creates an anti-electron and electron pair that can affect your results of the experiment. So it has to be taken into account. But how they can conclude that's the error, that's the function? Well, that's easy. 2 weeks prior to the experiment, they take all the data with the same arrangement, and 2 weeks next to the experiment, they take all the data of this cosmic radiation, so they can fit an error or function error of this cosmic radiation and subtract it off from the results. But then that's it. We found a new boson, we found a new force. It's a great discovery. Well, not quite yet, because yeah, they took into account all the errors or source of errors that are independent of the experiment, like the cosmic radiation, the standard deviation, and things like that. But there can be a systematic error, something in the laboratory that's are making something new or something like a new discovery, but it's not. So it has to be taken into account and make more experiments to verify if this is true.
Hello, my name is Raúl Ávila, and I will talk about the X17's particle feature. This particle has gained the attention of scientists worldwide. However, many of them still remain skeptical about the existence of such particle. Some experiments seem to have proven the existence of such particle. However, there's still very few of them, and they have mostly been carried out by the same team led by Krasnahorkai. Therefore, in the following years, more experiments will be made in order to accept or refute the existence of such called fifth force of nature. Among these experiments, one of the most exciting is the Na64 experiment at CERN. It will take place in the world's largest particle accelerator, the Large Hadron Collider, a 27-kilometer long loop packed with magnets whose electromagnetic fields are used to accelerate the particles and direct them through each lap. The process begins at the linear accelerator. Then the protons go through the proton synchrotron booster, the proton synchrotron, and the superproton synchrotron. 3 loops increasing in size, which continuously accelerate the protons. Then these group of protons will be divided into 2. Each group will go to the Large Hadron Collider at nearly the speed of light, circulating in opposite directions in order to create collisions. Using state-of-the-art sensors, scientists at CERN will look into the energy, or rather the missing energy of these collisions, in order to see if it is possible to link this missing energy with the X17 particle. However, this is not the only experiment that will take place in the next few years regarding the X17 particle. Other research facilities are currently looking for ways to prove that the X17 particle either exists or does not exist. Experiments such as the PADME experiment, the Meth experiment, the LHCb at CERN, and a couple more at the Jefferson Laboratory will all take place in the next few years. The results will mark the future of the X17 particle.